We got two questions on worksheet number 7 that we want to go over here today. Two questions that were due for homework last night. Two questions that both involve adding vectors together with funny angles. Now, if there's one thing that you remember from yesterday, it should be a 5-word phrase. What is that 5-word phrase? I don't like funny angles. Good. I don't like funny angles. In both question number 9 and question number 10, the questions that we had for homework last night, we've got at least one funny angle. By funny angle, we mean a non-90 degree angle, a non-right angle. So 30 degrees, 50 degrees, 60 degrees, 21 degrees, whatever the case may be. We don't like funny angles, so what we want to do is get rid of it, take it off to the side, box it off, get rid of it, and then turn the question into a more straightforward question where we have just right angles. All right, the first one, question number 9, involves a 30-degree angle. That's a funny angle. We don't like funny angles, so we take it off to the side. Now, what a lot of people do when they see this one is say, look, I already have the x component of that 50. It's 75, right? Like that's the horizontal component of it already. That's wrong. Okay, the horizontal component of the 50 cannot be bigger than 50. Think about that. The hypotenuse is 50. You can't have an opposite or adjacent side that's bigger than the hypotenuse. So that can't be. That 75 meters, that's a separate vector. That's completely independent of the 50. If I drew the 50 over here like this, and I didn't draw the 75, then you wouldn't say the x component of that is 75. So why would we say the x component of it is 75 over here? Two separate vectors need to be dealt with completely independently of one another. So let's take the 50 over here to the right. Let's label it 50 meters here. Let's label my angle right here. This is x, this is y, and let's find the x and y components of it, doing what we always do, not trying to cheat and take a little shortcut and saying, oh, it's 75, which would be wrong. All right. Which side of the triangle is the x component there? Is it opposite, adjacent, or hypotenuse? It's adjacent, yeah. It's adjacent. We have adjacent, we have hypotenuse. That's going to be which trig function, Christian? Adjacent and hypotenuse is? Good. So we're going to say cosine 30 degrees. Cosine 30 degrees is equal to adjacent over hypotenuse. And when I do that, I think I end up with 43.3. Okay, there's the x component. The x component of that 50 meters. And now what about the y component? Well, that's going to be the opposite side, right? Opposite in hypotenuse goes with which trig function? Gabe, which trig function is opposite in hypotenuse? Good. So we're going to say sine 30 degrees is equal to y over 50, or opposite over 50. The y component ends up being equal to 25 meters. There we go. There's the y component. Next thing I do is box it off, just to separate it, telling me that this is not really the main part of the problem. This is just a little tool that I have to use in order to get to the main part of the problem. Now, some people, we talked about this yesterday, some people like to scratch this out now, or erase it, if you have it drawn by hand, and then replace it with a 25 down and a 43.3 to the left. How do we know that it's 25 down and 43 to the left, Riley?
Is that original line thing? Whatever was down and to the left.
Good, good. We look at this and say, like, I don't know, I get 43 and 25. Like, how do I know whether it's supposed to be positive or negative? Like down, right, left, whatever? Look at my original picture. Yeah, I got 50 meters right here. Let's get rid of that again. 50 meters. It's down and to the left. Okay, if I'm breaking a vector that's down and to the left into x and y components, then one of them is going to be down and one of them is going to be left. So when I go to add them up, they'll both end up being negatives when I do the x and y components. Let's do the x and y components now. Okay, let's go through all of these vectors here. What's the x component of the 50 meters? Colton, what's the x component of that 50? Negative what, sorry? No, this one right here, the first 50. Yeah, sorry, there's a second 50 there, but I meant the first one there. Yeah, exactly, good. What's the x component of the 75 meters? Daniel, what's the x component of that 75? Good. And what's the x component of the, Colton, what's the x component of the second 50 meter vector? Good. Good. Negative 43.3 meters. 43.3, like over here, we've clearly identified that it's 43.3. Colton recognizes that it's negative because it is, well, it's down and left. So because it's left, it's got to be negative. 75 plus negative 43.3 is going to give me 31.7. Is that right? 31.7 meters. Now, do the y components. Kira, what's the y component of that 50 meters? Of that first 50 meters right here? Almost. Yeah, we're going to make it negative because it's downwards, right? Good. What's the y component, Sam, what's the y component of that 75 meters? Good. And what's the y component of that second 50-meter vector? What's the y component of that second 50-meter vector, Max? Yes, well, almost. We're going to make it not 25, but yes, 25 meters down, so it's negative 25 meters, right? Add those up, we get negative 75. Does that make sense? You get negative 75. Okay, good. Now comes the easy part, right? Now comes the, it could be grade 10 math, I guess. Some of you, it's a year ago, but let's say 31.7 over to the right. We know that's to the right because it's a positive x, plus 75 down. We know that's down because the y component is negative. Notice those two vectors are drawn blank to blank. Head to tail, head to tail. Vectors need to be drawn head to tail, except for the resultant vector, which is the sum of all the vectors, which is always drawn from start to finish. Sometimes I draw that as another color. Sometimes I might choose to draw it as a dotted line. You don't even have to draw it as a dotted or different color. It can be just a solid black line. Okay, but in the end, it's kind of useful to make it look a little bit different so that we can make it a little bit easier to see that it's the resultant or the sum of those vectors. We'll call our angle theta. Where are we going to label theta? Position 1, 2, or 3? 1, 2, or 3? It's position 3, yeah. Always draw the angle at the start of the vector diagram. All right, let's solve for r now. It's the square root of 31.7 squared plus 75 squared. Let's say square root of 31.7 squared plus 75 squared. Notice I didn't even put the negative in for the 75 here. Doing the Pythagorean theorem, just drop the negatives. We get an answer there of 81 meters. That's the magnitude of the resultant vector. Theta is going to be the inverse tan function of opposite over adjacent, 75 over 31.7. What kind of angle do you expect here? A big one or a small one? Yeah, it's going to be pretty big, right? Our y is quite a bit bigger than our x, so we are going to get a number that's bigger than 45 degrees for sure. 67 degrees? Yeah, and what is that? 67 degrees what of what? Mason, what is that? Is that east of north? Is that north of east? Is that, what is it? Yeah, we went south and we went east, but our angle is measured from the east. Right? We have this resultant vector that's measured, theta, measured from the east vector. So it's from east, of east, south from east, or south of east. How'd you drawn the vector diagram in the opposite order? 75, then 31.7? That would have been correct, because you still could have drawn that head to tail. You would have gotten 81 meters at 23 degrees east of south, which would have been also a correct answer. It would have meant the same thing. All right? How many people ended up getting that? 81 meters, 67 degrees south of east. Yeah. Was it empty though?
Yeah, it was empty.
No. A little bit of water in the bottom there. All right, let's take a look at number 10 now. Here we have two funny angles. Here we have to do two off to the side, boxed off vector analyses. Two funny angles that we say, I don't like funny angles to. Let's do the 5 meters first. 5 meters, we got 60 degrees labeled right here. This is going to be X, and this is going to be Y right here. Remember, our triangle has to be drawn around the angle. Now, which side of the triangle is X component this time, Jack? Is X, the X component opposite, adjacent, or hypotenuse?
It's opposite.
Good, it's opposite. Okay, Y is adjacent because it's touching the angle. The 5 is the hypotenuse because it's also touching the angle, but it's the longest one. So X is the opposite side. We're going to say sine 60 degrees is equal to opposite over 5.0. X is therefore going to be equal to 4.33. There's my X component, and my Y component, we're going to say is, well, it's going to be cosine 60 degrees is equal to adjacent over hypotenuse. Adjacent side equals 2.5 meters. Let's box that off. We're not done there because we still have to deal with the other one, but let's erase this and replace it with 4.33 and 2.5. Remember, guys, we've said this all day yesterday. I want you to show all of your work. The one thing that I can forgive you for not showing is the replacing of the 5 meter vector in here with the components. Okay, if you have them shown over here, then I can live with you not redrawing it. If it's helpful to redraw it, then redraw it. But you don't have to. You do need to show everything else. Don't skip steps. Okay, let's look at the second vector now, this 10 meters, because it's also at a funny angle. 10 meters, we got an angle of, this is X, this is 30-degree angle here. This is my Y component. This time, X is which side of the triangle? Ernesto, is X opposite, adjacent, or hypotenuse this time? Good. It's the one that's touching the angle, but not the hypotenuse. So we're going to use cosine 30 degrees is equal to adjacent over 10. X equals 8.66. And we're going to say sine 30 degrees is equal to opposite over hypotenuse. And the opposite side of the Y component ends up being equal to 5.0 meters. Let's box that one off as well. And if you want to, replace this with 8.66 and this one with 5. And then we can completely get rid of that. Now, look, now we got a nice, well, relatively straightforward question where we just have X's and Y's. We don't have to deal with that funny angle anymore. Remember, the funny angle is gone forever. It's out of our lives forever and ever. So now we break it into X's and Y's. As I was walking around checking your homework today, there was a lot of people that didn't show this, didn't show the X's and Y's. Show it. Show it. You need to show it. The X component of the first one. Mason, what's the X component of the first one there, that 10 meters? Good? Mackenzie, what's the X component of that second one, that 10 meters? Good. Coley, the third one here? 4.33. Not 5, right? The 5 is dead. Okay, we replaced it with a 4.33. What about the next one, the 10-meter one? Victoria, what about the 10-meter one right here? Good. 8.66. Negative 10 plus 4.33 plus 8.66 is, I think it's negative 3, isn't it? 2.99? Negative 10 plus 4.33 plus 8.66. What does the work out to be? Positive 2.99. Now let's do the y components. How much of the first one is y? How much of the first one is y, Tyra? 0, good. Dexter, how much of that second one is y? This one right here. How much? Sorry? Good. -10, good. And then we got that third one that was 5 meters, but that 5 is dead to us. So how much of that 5 meters? It's 2.5, yeah. Good. And that fourth one that was 10 meters, which is now gone. Colby, how much of that 10 meters is a y component? Good. -5, because we have it drawn downward, right? And we knew to draw downward because the 10 meters was to the right and down. So we add these up. This one's easier to add mathematically. It gives me -12.5. Right? And now we're just going to redraw this. 2.99. 12.5 goes down. By the way, I could have drawn this. Is that correct, by the way? Head to tail? Yeah, that's right. Could I have drawn it like this? Absolutely. Absolutely, I could have drawn it like that. Just my angle would have been the complement of the angle that I get here, right? 90 minus that. Draw whichever way you want, doesn't really matter. My resultant vector is drawn from start to finish. We're going to label that R. And we're going to label theta where? Position 1, position 2, or position 3. Where is it? 1. Yeah, always at the start of the diagram, right? Let's say R is equal to the square root of 2.99 squared plus 12.5 squared, square root that. What do I got here? $12.9. We're going to make that 2 digits, 13 meters. That's the magnitude of the resultant. But we got to find the angle as well. The inverse tan of opposite over adjacent. Oh, you know what we forgot to do first? What's the first thing that we should always do? The first time we do a trig calculation each day, you don't need to do it 20 times a day, but once a day, the first time you do a trig calculation, hey, what should it be? Sine 90. Well, we know we're already in degree mode because we've already used trig already, but we should get in that habit. Sure enough, it's 1. So we're good to go. Inverse tan of 12.5 divided by 2.99. We get 77 degrees. And we're going to record that 77 degrees, what of what? Yeah, it's going to be south of east. We're measuring the angle from the east, but yeah, we're going south from the east, so it's south of east. Had you drawn it the other way, you would have gotten 13 degrees east of south. How many people got 77 south of east? How many people got 13 east of south? Anybody? Yes? Okay. Both are 100% correct, right? All right. Remember that I can ask you this question that was just asked in a number of different ways. Okay, this one asked you, who's got the worksheet in front of them there? This one said, add the following vectors. Okay, add the following vectors. That's what we did. It could have also said, and meant the same thing, find the resultant vector. It would have meant exactly the same thing. It could have said, find the total displacement. Because they're displacement vectors. To find the total displacement, I have to add those vectors, right? All means exactly the same thing. The one thing that I could ask that would actually be different would be find the total distance. If I said find the total distance, how would this question be easier? Like, how would it be way easier? How would it be way easier, Riley? Yeah, you just add the numbers together as scalars, right? You wouldn't pay any attention to direction if I said find the total distance, right? Find the displacement, vector. Add the vectors, vector. Find the resultant vector, vector. Find the distance, scalar. Don't worry about any of that direction stuff, okay? Honestly, I'm not likely to ask you that, right? Because it's too easy. unless it's a little bit of a trick question as a multiple choice or something like that. You know, pay attention for that, but odds are pretty good you won't be asked that. I would like you now to take a look at two examples that are in your notes here. Example number 15 and example number 16. How are these different than the questions that we've done over the last couple of days? Not much different at all. Like mathematically, fundamentally, they're the same thing, except that in these questions, the vector diagrams are not given to you. So you need to draw them first and then do the analysis. All right? So let's go at those now. Let's draw this first one. 100 meters to the west. That's 100 meters to the west. Then we got 50 meters to the south. This is 50 meters to the south. And notice that it's drawn head to tail. Then we've got 20 meters to the east. That's 20 meters to the east. Again, drawn head to tail. And then we've got 30 meters to the north. That's my 30 meters to the north, and it's drawn head to tail as well. Let's draw that second one. The sum of the following vectors. Same thing as add the vectors together. Same thing as find the resultant vector. We've got 10 kilometers to the east. Then we've got 20 kilometers at 30 degrees south of east. This vector is going south and east. Right, south and east. It's 20 kilometers. And this angle right here is 30 degrees south from east. Right, measured from the east, south from east, or south of east. And then we've got a 15 kilometer south. So it's going to look something like this. Now, could I have drawn these in different orders? Absolutely, absolutely. Like this second one, it would be a little bit odd to do that because of the way that they have it listed in the question, but we could have absolutely said 15 kilometers, then 10 kilometers, and then 20 at 30 degrees south of east. It wouldn't make any difference. Draw them whatever order you want, as long as we have them drawn head to tail, except the resultant. The resultant vector is always drawn from start to finish. And once we have those drawn, we do our thing. We get rid of a funny angle. We replace this with this, and then we got a right angle triangle. We do our thing.